क्या हो गया है? Okay, so when we are talking about the designs, so there are basically we categorize the design to the three parts: SOC, ASSP, and ASIC. So we usually talk about the ASIC, application specific integrated circuit. So if you will see, like, okay, most of the time we usually talk about the ASIC flow, ASIC related job. So what is ASIC? It's a application specific integrated circuit. And the ASIC, there are two portions. We usually divide the industry in a full custom and semi-custom. Now, what is a full custom? Full custom, as the name says, fully customizable ASIC. That means even if you are talking about the standard cell. So those who don't know about the standard cells like logic gates, if you're talking about like AND gate, NAND gate. Now, AND gate, NAND gate, obviously with the help of the MOS, CMOS, you can just design it like with the help of NMOS and the PMOS. Then the layout of NMOS and the PMOS. So in the layout, when we are talking about, so there is a width, height of a particular NMOS and PMOS. So for example, if I'm talking about, so it's like, maybe if you remember, we usually draw something in this particular way. Okay. So there is a P, this is basically the poly. Then we usually talk about like, okay, this is my PMOS area. This is my NMOS area. And then we talk about this. So in this, what we are going to do, we'll say like, okay, this I'm going to connect. This is again, I'm going to connect. And this is my output. This is my input. Now here, maybe you have one more layer, which is a NVEL. NVEL, then P plus P plus, and then the poly. And then there are the connections. These greens are basically the connections. Now this is just a simple layout. I just draw it the simple layout. Okay. Now this layout, I can draw it in this particular way also. So here, this is also the layout. Am I right? So what is the problem here? There is no problem. But if you will see this, there is no symmetry, nothing is there. So if I will talk about between these two layout, both are the layout, both have the layers, both can work in a one way or other way. Maybe the specifications are going to change. But when we are talking about the standard cell, that means something is standard in this particular layout, which may be not standard here. So when we are talking about the standard cells, so standard cells, basically when we are talking about the standard cells, usually we talk about the standard in terms of the height. So height is going to be the standard, and then we draw the layout. So I will explain that particular part later on today itself. Like, okay, what is the meaning of a standard cell and how it is going to help you in the physical design. But what I'm just trying to help you in terms of the fully custom. So fully custom, there is nothing as a standard. Okay, everything you can design as per your specifications. So if you are thinking like, okay, I just want to make a P area bigger and area smaller, you can do that particular part. If you just want to do the reverse, any height, any weight, you can do anything. So there is from the shape point of view, nothing is standard. It's just like I just want to achieve a particular logic functionality wise from the current, from the voltage, whatever I just want to achieve, I will achieve it with in my layout in that particular design. So that is a fully custom. So fully custom in the sense everything you are going to customize as per your requirement. So that type of design is known as a full custom ASIC. Now, if everything you're going to design, so that means from the designer point of view, you need more expertise. You need you need to understand each and everything. Okay, how it is going to impact the standard cell, the input output characteristics, everything. Okay, then it will take a lot of time, because there is nothing standard. It's not like drag and drop. You just create a structure, drag, drop, and it is ready. It's basically you have to first, for each and every design, you have to prepare it. You have to customize, or you can say you have to just do from the very scratch. You have to do that particular part. So that is a fully custom. It is a time-taking process. Second one is a semi-custom, where something is you're going to design, something is already ready. So there are three type of, again, design, which is like standard cell based. I just described you. So basically here what happened, all the logic gates, all the logic gates, if you are talking about the sequential elements, combinational elements, most of the time these are we prepared in advance for each and every technology node. So for each and every technology node, you already have these somewhere, and that somewhere is known as a standard cell libraries. So that means you will create a set of a library. We will say like, okay, for this 40 nanometer, this is a set of a library where I have all the logic gates. And then you will say like, okay, how that logic gate is going to fulfill my requirement. Then I will say like, okay, no problem. I have the 10 different version of logic gates. So inverter, there are 10 different version of inverters. NAND gate, 10 different versions of a NAND gate. Now, what is the difference in those versions in terms of the specifications? Maybe one is going to drive 2 gates, another is going to drive 4 gates. From the voltage point of view also, maybe one the is like on a voltage level is different, another voltage level is different in terms of the threshold voltage, in terms of the power, in terms of the delay. So there are going to different specification. You are going to design it, but you're going to design in advance, and then the designer is going to use them as it is. So they are not going to customize it. They will just use it. So if in your library, there are the 10 different type of inverter, then you don't have any other options to use the 11th kind of inverter. So you have to design your chip based on those 10 different inverters only. So that's basically the standard cell based ASIC if you are talking about. Similarly, there are gate array based, or we can talk about in terms of programmable ASICs. So these are basically, if we will talk about in terms of programmable ASIC or the gate array based ASIC. So maybe you have seen this FPGA part and all other things. So there is a another category. So maybe in your college days, you have gone through this channel gate array, channel-less gate array, PLDs. Maybe you have seen all these things. You have studied this particular part, FPGA. If you haven't studied this particular part, maybe what you can do, you can just go back. Maybe you can just refer the Cedra Smith, and the Cedra Smith, you can just check it. This channel gate array, channel-less gate array, or maybe just search on the Google. You will get all these things. Just have a basic idea. Like, okay, what are all these different type of designs? So this is basically, if you will see the in terms of the industry, if we are talking about the analog side, so most of the time in analog, we are working here full custom. So here basically the analog. When we are talking about the digital, people are working on a standard cell based design. And the current industry, because from the time to market point of view, FPGA is the good one. So basically in FPGA, everything is ready. You have to just burn it. You have to just program it. You have to do in that particular way. A standard cell based design, you have to design each and everything. But yes, there are the certain components which is already available. Fully custom in the sense, you have to, from the scratch, you have to do everything. So from the time to market perspective, also FPGA is a fast, but you don't have a flexibility in terms of the size. Standard cell is basically the second stage, is it take times, but you have a flexibility in terms of the size. Fully custom, it will take a lot of time, but you have a lot of flexibility in terms of the size. So you can do in that particular way. SoC, system on chip. In the next slide, I will explain you what is the SoC part. ASSP is a similar kind of thing, say application specific standard part. So till now we are talking about application specific integrated circuit. Now we are talking about application specific standard part. Okay, some small parts you can design it, but that is as a part of your IC. So like we were talking about some standard part, let us suppose if you are saying A to D converter. So as such, A to D converter is a part which you can use it in a multiple ICs, not the multiple ICs, in a multiple circuits. But now you're saying like, okay, A to D converter, I'm going to prepare as a part of a chip. So, but that is a part basically. So that's we are saying it's the application specific standard part. It's a standard configuration. Now let's talk about the SoC. So as the name says, silicon on system on chip. Now what is a system on chip? So if you will see these two diagrams, then you can easily figure out what I'm talking about, the system on chip. So there is a there was a time when still right now. So maybe if you have seen in your mobile, there is a PCB board. In the PCB board, there are a lot of chips are there. Okay, so in that particular chip, there may be some processor, maybe some DSP processor is there, maybe some memory is there. So what you are doing in that particular PCB board, you are adding all those PCB, like all those ICs. So like here you can see there is a ASIC, there is a microprocessor, DSP, memory, interfacing unit. So all these are the chips which you are going to put on a PCB. You are going to make the connections here. So that is the system. Now that this is going to create a system, maybe your, for example, mobile phone, or maybe your laptop, or maybe something related to the board of your the washing machine. But tomorrow you came back and you said like, okay, Puneet, I just want to reduce the size. So how you're going to reduce the size? You will say like, okay, let me do one thing. In place of creating these chip individually, I will create all these functionality in a single chip. So right now, if you will see, this is my some processor. In this particular processor, this is basically the packaging. After that, these are the chips. Sorry, these are the pins. Okay, this is the DSP packaging. These are the pins, and then you are going to make all these connections, all these PCB connections. Okay, you will do in this particular way. Now, what you are saying, like, okay, in my in a particular chip, this is going to be my DSP block. So now this become a block. So now what exactly you are saving here? You are not going to do the packaging of this DSP. Only the functionality of the DSP is here, or you can say the core or the whatever be inside this, whatever the logic is there, inverter or gate and everything, that's going to be here. But you are not doing any packaging. Okay. Same with the memory, you are not doing any packaging. Now, whatever the connection you want to do it, internally you will do the connections with the metal 1, 2, 3, 4. Here, if you will do the connection, you have to do the connections with the external wires. Here, whatever the connections you want to do it, you will do it with the metal 1, metal 2, metal 3 in that particular way. So if roughly, if I will see packaging and the pin, I'm saving here in this particular case. There is no packaging, there is no pins, external pins are there, no external wires are there. So that means the size of my SoC is going to be compact, or you can say the less compared to this particular part. Am I right? Okay.
Yes, sir.
Great. So, but the other aspect is it become more complex. So in SoC, it become more complex because the functionality has increased. Apart from the complexity, there is another problem. Let us suppose in SoC, tomorrow DSP stop working. Then what you have to do, you have to say, you have to throw away this entire chip. In this particular case, if the DSP is not working, you can replace this DSP with the other DSP also. So now, maybe if you will see, there is a right now, if you will just go into the market and if you just say like, okay, I need a desktop, high configuration desktop, if I'm talking about. So the size of the desktop is very big in Indian market right now. Maybe, and it will come around 33,000, 40,000, you will get a decent desktop. Then the monitor and everything is there. But have you ever heard about the Mac Mini? Mac. So basically Mac, Apple have a product which is like in a very small, just like in the size of your hand. That's all. And within your that palm, basically you have everything. So that means it has the memory, processor, hard disk. It has everything there. And it's a very, very small. It's just a size of a your palm. That's all. So what exactly they have done? So in your desktop, there is a card. In that card, you have the RAM, memories, SSD. Yeah, everything is an externally. You're going to uh, connect with that particular board. Here, everything is within the chip itself. So that's the reason it is known as the system on chip. So that's basically I'm talking about what is the difference in a normal system and when you're going to talk about the SOCs. That is the thing. So if tomorrow, if anyone is saying I'm working on SOC, now you know what is the meaning of the SOC. SOC is not something very fancy word. It's just like in a buzzword people are talking about, but it's a normal chip. So if you're tomorrow, if you're working on a processor, or if you will say, like, okay, I'm working on SOC, it's the same thing. So from the flow point of view, from the design point of view, from the VLSI point of view, it's the same. It's just like complexity is going to increase. That's all. Online guys, is it clear? Anyone have any doubt?
Yes, sir. Clear, sir.
Clear.
Okay.
Yes.
Good. If it is clear to all of you. Okay, let's see if I can switch on my camera. दिखाई दे रहा हूँ क्या?
No, sir.
Okay. Am I audible now?
So,
Okay.
yes,
So
Yes, sir.
now let's talk about the VLSI design flow. So as a part of a VLSI design flow, let's try to understand each and every step. And this is something is going to help you to understand this physical design also. So you can easily connect the dots like, okay, what is going on there and how things move out. Now, the first thing is a system specification. So just in the previous slide, we have discussed about the system. That's what we are talking about, the system on chip. So that means now we are talking about the system. So what is the specification of the system? What kind of system we want to design? So let us suppose if you want to design a system for your we are saying laptop. Okay, so laptop or the mobile phone. So what is the specifications we usually look for? Like, okay, how many cores are there? What is the frequency? Okay, so like, okay, in this particular frequency my phone is working. What is the power consumption? Power consumption in the sense like, okay, what is the talk time? What is the ideal time? If I will just see the recordings, videos, then what is the time? So basically now we are talking in terms of the power consumption. So then we say like, okay, this is the power consumption for this particular battery. This is going to be happen. Then we usually talk about like, okay, in terms of the display, then in terms of the timing, like, okay, how fast, how slow it is, how many functionalities are there. So all these things we usually talk about. And what is the size of my phone? Not the design. What is the size of my phone? So we usually talk about in the system specification, once the functionality, then in terms of the power, then in terms of the speed, and then in terms of the area. So we are talking about the four main things: area, power, speed, and the functionality. Is it clear? Now, once this portion is done, like, okay, my system specifications is defined, the next step is how I'm going to design architecture point of view. So like in a layman language also, if I will ask you like, okay, you have to design a, like you have to construct a house. So the very first question come like, okay, when we talk about the construction of a house, we say like, okay, what is the size of the plot? Okay, that is the one thing. But before that, we usually talk about like, okay, how many rooms we are going to design it. Okay, it's a 2 BHK, 3 BHK. Are we going to design a, like construct a house in such a way like, okay, they're going to be in an open area. If we have the car, like, okay, the porch will be there, the 2-story, 3-story. We usually talk about all these things. So that is basically we are talking about the specification. Then we are talking about the architecture. Okay, specification is done. We know like, okay, now I need a 2 BHK, but that is on a first floor, sorry, ground floor. First floor also, there should be 2 rooms. The third floor also, there should be 2 rooms. And then we are saying like, okay, in the ground floor, maybe we can have a dining room, we can have a hall also. So those specifications are done. But now question is, how beautifully we are going to design it. So the architectural design, that is basically now you're going to define the architecture of your whole chip. Now architecture of your whole chip. Now the chip point of view, what happened? Do we are we going to use this particular chip for the speech processing? So that means if you are going to do it for the speech processing, that means the speech related processor supposed to be there. If you are talking about the image processing, that means the image processing related processor is supposed to be there. So we usually talk about uh, what kind of accuracy we need it. So maybe you have studied about the filters. Now in the filters also there are the different configurations. There are the, in a DSP also you will see like, okay, floating point architecture. Okay, some processors are basically for the computation of the floating points. Some is only for the integer related thing. That is a one portion. Second portion is whether it's supposed to be 64-bit or the 32-bit. I think all of you know, like, okay, when we usually install a software, it usually asks like, okay, what is the architecture, whether it is a 64-bit or the 32-bit. And based on the 32-bit and the 64-bit, the softwares usually become different. So that means architecturally, how you have defined it, that is important. If you will search on the Google, if you just see it, there is something like, okay, what kind of processor controller you are going to use it, like ARM memories you are using, ARM processor you are using, Intel you are using. So basically the internal architecture of a particular chip or whatever you're using it. So if something you have defined it like, okay, I'm going to use it as it is. So that particular portion, basically you have to capture it at this particular point. Now you may be thinking like, okay, how it is going to help you, or maybe how we are going to do that particular part. So I'm just taking a one example and maybe try to understand from that particular example. So for example, if I'm saying like, okay, there is a 4-bit adder versus 16-bit adder. Now, what is the difference between the 4-bit adder and 16-bit adder? So for example, in the 4-bit adder, you have designed it in this particular way. So this is basically A0 to A3. This is B0 to B3. This is your sum S0 to S3. And this is your carry. So this is my 4-bit adder. Or maybe you will say like, okay, one carry C in 4-bit full adder is this. Same thing you can design as a 16-bit adder also. So you can say like, okay, A0 to A15 and B0 to B15. Then one C in, same S0 to S15, and one is carry. Now let's see what is the difference between 4-bit and a 16-bit? Same thing you can understand from the 16-bit and the 32-bit, or the 32-bit and 64-bit. Okay, same difference, you can understand it. Now in my processor, in my ALU, maybe I want to do 4-bit addition, but there is a scenario where I want to add a 8-bit addition. So I want to do the 8-bit addition. 8-bit addition in the sense, I have a data from B0 to B7, and I want to add it with the A0 to A7. Now you want to add this using this circuit. You want to add 8-bit data using a 4-bit adder. Now how you are going to design your circuit? So obviously using a 4-bit adder, you cannot add the 8-bit just like that. What you have to do, you will say like, okay, Puneet, there is only one option because I have a 4-bit. I will divide this into the 4-bit, B0 to B3 and B4 to B7. So first step is divide, and then you will just give here the 4-bit here. You will just give 4-bit here. Same here, 4-bit. You will get some data as a S0 to S3. Am I right? Then you are going to save this data in a register. So maybe you have a register which is a S0 to S7. So first you will save it here. So first 4-bit you are going to save. So I'm just considering this as a single cycle. In the first cycle, you are going to, in a clock point of view, I'm saying, in a one cycle, you are going to save, you are going to do the 4-bit addition. You are going to save that particular output in a output register and done. Then in the second cycle, you will give this set of a data here again, and then you will get the output here. So that means in a 2 cycle, now you are able to do the addition. So from the programming point of view, from the structure point of view also, there should be certain registers or the certain memory location, which is the 8-bit. In that particular 8-bit, now you have to make sure like, okay, the program which you're going to write it for the addition, it should be like, okay, first divide into the 4-bit LSB, okay, LSB portion, then the MSB. So they're going to be a shift registers, they're going to be a normal registers, you're going to do in that particular way. Now, same 8-bit addition, if you have to do using the 16-bit adder, then the concept is different. Now, in this particular case, what you have to do, you have to just say like, okay, I'm going to do the addition in a 16-bit adder from A0 to A8. That's all. And the rest of the portion, I'm not going to use it, or maybe we will say like, okay, we are not going to, we will just give the output as a 000 or something. We have to see in that particular way, like, okay, what architecture, what programming we are going to do it. Is it clear, everyone? Online people?
Yes, sir.
Yes, sir. Yes, sir.
Yes,
Yes, sir.
yes, sir.
Yes, sir. You are not audible again.
Am I audible now?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah, so I'm just saying like, okay, is it okay now?
Yes, sir. Now it's okay.
Yes, sir. It's
Yes.
okay.
Is it clear?
Yes.
Yes, sir.
Yes, sir.
So how
Yes,
the
sir.
architectural design is important from the chip perspective, is it clear? Like, okay, your programming and everything is going to be different in case of the 4-bit or the 16-bit, 32-bit, 64-bit. So it is very important at this particular stage itself, like, okay, you should know, like, okay, what should be the architecture. Okay, great. Now let's talk about the next step. So once the design is confirmed, then your Verilog code come into the picture. Now you know how to design the circuit. So right now, as an engineer, our understanding is like, okay, we are going to design the circuit with the help of like truth table, and then we will just directly design a circuit. Yes, for the adder, it is very easy. You can say like, okay, there would be a AND gate, NAND gate, OR gate. We will give the 2 input, 4 input, and you can come up with some adder circuit. But obviously, you know, like, okay, in a bigger design, it's going to be very difficult just to do the circuit designing right straightforward. So for that, we have this RTL coding, RTL designing. So this functional design, the logic design, where we just write a code as a either in a behavioral or maybe the structural, depending upon the Verilog, whatever you want to use it, we do it in that particular way. So that portion comes as a part of a functional design. So Verilog is important from that particular point of view. From the Verilog, once the Verilog is done, then you can easily convert it into the circuit design. And circuit is basically, now we are talking in terms of the gate level representation of your functions. Now, what is the difference? You can say, like, okay, why I can't directly prepare a circuit? Why there is a need of a Verilog or a particular language? Now, your understanding was there is a function you want to do the as a AND gate. You are saying, okay, there is a AND operation you want to do between the A and the B. So as a part of a language, you can write in any particular syntax. You can say, okay, A and B. This is also, I can understand, like, okay, you want to do the ANDing between AB. Or you can say, okay, this is dot is considered as a AND. I want to do A dot B. Or maybe you can come up with some other language, some other syntax. You can say, like, okay, I just want to do the operation AND between A and B. But the point is, from the circuit point of view, at this particular stage, you're not supposed to think about the delay. You're not supposed to think about the area. You're not supposed to think about in terms of the power of this AND gate. You're not supposed to think about like, okay, in my final circuit, what kind of AND gate I'm going to use it. So for example, you can say like, okay, this is my AND gate. This is also my AND gate. If I want to implement this with the help of the OR gate, basically inverted. So it's like A dot B bar and the bar, which is equals to A bar plus B bar whole bar. Am I right? So that means this is also my AND gate. If I'm going to design the AND gate with the help of the mux, I can design it with the help of the mux also. Now you can say like, okay, A, so you can say 0, 0, 0, 1, 1, 0, 1, 1. This is my A, B, AND gate is 0, 0, 0, 1. Then you can say like, okay, A equals to 0, Y equals to 0. So this is going to be ground. And A equals to 1, Y equals to B. This is my B. So this is also my AND gate. So that means now you have how many ways? 1, 2, 3, 4. So there are the 4 different circuits which can be used to design this particular AND gate. I'm just giving an example, okay? Now this conversion from this logic A dot B, how you're going to convert it into the circuit, it has a different reasons, okay? Maybe One circuit is because of the space, another is because of the delay, one is because of some other reasons, or maybe I don't know that particular part right now. And you're not supposed to think when you're writing a code. But when you're going to convert into the circuit at that particular time, it is important. And then we will give the rest of the input at that particular time. But at least from the functionality point of view, you're going to decide the functionality at this particular stage. And that's the reason we are saying functional design and the logic design. And then after that, now I'm going to decide the respective gate. That means the circuit. Then that's the reason we are saying it's a circuit design. So once you're going to design as a circuit, then the next thing is now my circuit is decided. Now I know like, okay, now I have to go with the inverted inputs, or I have to go with the NAND gate, or I have to go with the combination of a NAND and the inverter. Now, once this circuit is designed, now only the thing is I have to physically place this particular circuit and I have to create a chip. Now, how you're going to create the physically? So till this point, basically, you're doing everything just from the functionality point of view, or maybe some timing, delay, power, whatever be your basic understanding. But we are not talking about the size. Then I will say, like, okay, my chip is basically in a form of a rectangle. Now, whatever the circuit you have decided here, now you have to place that particular circuit here. Or maybe you will say, like, okay, my chip size is in a rectangle shape. That means now the same circuit, you can place it here. Tomorrow I can say, like, okay, no. So because this is the shape where I have to place this particular circuit. So this portion, which is the shape which you are talking about. So those who have attended the physical design class today, so it's like, come under the section of under the floor plan. Basically, once you're going to plan your floor. So from the house point of view, also it's the same thing. First, you have designed it from the blueprint, you have done it. And at that particular time, you're saying like, okay, now it's the time to physically draw it. So physical in a sense, now you have the land, you know the size of my land, and then in that particular land, how I'm going to place it. That is basically the physically design. So physically design, always remember when we are talking about the physically design, that means we are talking about the coordinates. We are talking about the exact shape. We are talking about each and every layer. We are going to talk about like, okay, this particular layer is going to be placed at this particular corner of my chip. So we are going to decide each and everything in the case of a physical design. Once you're going to design it physically, then you're going to verify it physically. Like, okay, after designing whether it is working as per the foundry requirement. So foundry is the company, they are going to fabricate. So they came up with a certain rules and they said like, okay, I'm going to fabricate only when you're going to follow all of my rules. So then you will say like, okay, I have designed it physically. Now I just want to verify whether I'm following all of your rules or not. If I am following all of your rules, then I will just hand over to you this particular design and then you have to fabricate it. So how you're going to do the verification? That comes under the physical verification. Physically, you're going to verify it. Second thing is, I asked you like, okay, this is the specification, the system specification, okay? So you have to check it whether the system specification is working correctly or not. So that comes as a part of a sign off. So sign offs, that means now I'm going to finally verify each and everything in terms of the power. If I will say power, then it will say power sign off. Timing sign off. If you are talking about functionality or anything, that is also come as a part of a sign off. Usually we usually talk about the power and the timing. हमें सब पे करना है. We have to do for power also, timing also. The flow of a power sign off is a different. The way we are going to do the power sign off is going to be different. Timing sign off is different. The tools are different. So you have to give the inputs and on the basis of that, they're going to do the powers. Physical verification. Yes. So you can do these things in parallel also. The question is, the output of the physical verification is going to be the part of a sign off. Answer is yes. So obviously once everything is physically correct, then you will say, okay, now let me see whether it is as per the specifications, meeting all the power requirement, meeting all my timing requirement or not. There should not be any problem there. And once that is done, that means now physically you are following all the rules. From the system specification point of view, your functionality is good. Your area is already meeting because you have done, you have followed that particular floor plan, the shape and the size. Power and the timing, you have checked it. Everything is good. Now you will select, okay, fabricate it. So Foundry is going to fabricate. Once they will fabricate with the help of the wafer and everything, after that they will select, okay, now I created a chip. Now let's do the packaging. So they will do the packaging. And then there going to be one more testing after that particular packaging, just to make sure like, okay, everything is working fine. Because whatever the testing you have done before the fabrication, that is with the help of the tool. So that is not the real testing. That is basically based on the tool. So you're doing the testing on the tool, the simulation and everything, you're doing it. But now we are not talking about that particular testing. We are talking about the hardware testing. Now you have the chip. Now you're going to test that particular hardware. Before that, everything is a virtual hardware, you can say. So you're doing all the testing virtually. Now you're going to do it really, in the real sense. So that is basically the packaging. After packaging, you will do the testing. If everything goes fine, then your chip is ready. So this is basically the whole flow in a very layman language. There is a one more step in terms of the backend and the front end. So architectural design, functional design, circuit design usually come as a part of a front end. So there we usually talk about the behavioral description, how you're going to write the code. RTL description in terms of the RTL. Functional verification, once you're going to write it, then you're going to functionally verify it. Then logical synthesis. So I told you, like, okay, there is a Verilog code. Now converting that into the gate level as a circuit level, that how you're going to do it. So Verilog code, you're going to synthesize, you're going to convert it. That is known as a part of a logic synthesis. I will explain this particular slide in like this particular step in once again. Then you will get the gate level netlist. Once you will get the gate level netlist, you have to do one more verification, which is a logic verification. So functional verification you have done first, just to make sure like, okay, whatever the code you have written, functionality is correct. But after that, you convert it into the logic gates. So you are going to do the logic verification. So you are going to do that particular part. So this is basically the part of a front-end design. After that, does physical design come into the picture? So in a physical design, we are talking about the partitioning. Now, what is the meaning of a partitioning? So maybe those who have seen this gated community, or maybe a lot of like societies we are constructing nowadays. So if I will say like, okay, I'm going to construct these societies just like that, okay, one by one, then you will say, oh, no, it's not going to work. It will take a lot of time. So let's do one thing, partition everything. So they partition it in terms of the tower. They said, okay, they're going to be the 20 tower. They're going to be one clubhouse, okay, and they're going to do some market. Now they have options like, okay, they can assign a different team, and they will say like, okay, one team is going to construct one tower, and one team is so all the 10 teams are going to 20 teams are going to construct the 20 towers, plus one team is going to do the clubhouse, one team is going to work on a market. So that means now we have a 22 teams and they're going to work at the same time. So obviously in that particular way, what will happen? The construction is going to be fast. Your whole society is going to be ready maybe in the next 1 year. There is another option. I will say like, okay, there is only one team. They are going to first construct one tower. Then they will move to the second, third, fourth. They can do in that particular way also. The third option, you will say like, okay, no, first floor we will construct for each and every tower. So there is no concept of tower. We will just put the one brick here, then the one brick next. It will take a lot of time. So in our design, when we are talking about the millions of gates, billions of gate, so then it is, if we are saying, okay, we have to design a chip in the 3 months, what are you going to do? You will say like, okay, divide it. So that comes as a part of a partitioning. I will explain you a little bit what is the meaning of a partitioning, okay? How, on what basis we do the partitioning. After the partitioning, then we have to plan it. Like, okay, now I have divided my whole chip into the 6 partition, where I'm going to place which particular partition. That is basically the chip planning. How I'm going to provide the supply, how I'm going to provide the water connections, okay, how I'm going to give the electrical connections, input and output, how many gates supposed to be there, how many pins supposed to be there. All those things I'm going to design or plan as a part of a chip planning. Now, once the chip planning is done, then is basically the placement. Now you're going to place it. Now you'll say, okay, now I'm just going to construct. Now I'm starting placing the bricks. That is basically the comes as a part of a placement. Now, as a part of a chip flow, so partitioning, the whole chip come into the blocks. So we usually say the term, we usually use the terminology is a block. So this is my chip. In this particular chip, I'm going to do the partitioning. I will say, okay, there are the blocks. So block 1, block 2. Or maybe you have said like, okay, this is a block 3. So that comes as a part of a partitioning. Then you say like, okay, where I'm supposed to place it? Again, the block 1 is here, or the block 1 can be placed in the bottom. That is the chip planning. Now, this is the block. Now you have to place the logic gates also. So the placement is a stage where we usually put the logic gates. That means this block is basically what? So for example, this particular part, you have divided it. Now this inverter you have to place in this particular block. Where exactly you're going to place the inverter here? At this particular position here, maybe one inverter is going to be placed here. Maybe the one inverter is going to place here. So that comes as a part of a placement. So standard cell placement is known as a placement stage. Now block placement is basically the part of a chip planning or the floor planning. So chip planning and the floor planning, these are the interchangeable words. Okay, then the placement come into the picture. Now once the placement is done, then the next step is the clock tree synthesis. Now, before we understand the clock tree synthesis, always remember there are the 3 types of signals. There are 3 types of signals. One is a power signal. Another is a clock signal. Third is your information signal, or we usually say the data signal. So power, VDD, VSS, this is the constant. So we usually plan it at the chip planning stage. This is a very important, because if the you will not get the power, then your chip is not going to work. So you will make sure like, okay, each and every IC transistor should have a power. So that comes as a part of a power planning. So floor planning, power planning combined, we are saying the chip planning. Now that is done. The second important signal is a clock. Because if your whole circuit is not synchronized properly, then there is a problem. So that means the second step you have to follow, you have to plan the clock signal. So you have to properly route it. You have to properly just connect the different circuit, different memories, or different registers, different flip-flops in such a way, like, okay, they should be synchronized properly. From the routing perspective, there should not be any issue. Once the clock is going to build, clock tree is basically the terminology. I will explain you what is a clock tree, but once the clock is going to build, or you can say like, okay, now the clock supply and everything is done. The next step comes for the signals, which is like signal routing, data signal routing. So that's the signal. And what is the data signal? The information. We are saying 1010, okay, the output of a AND gate is this, and the 2 informations are like this. So whatever be the data information we just want to manipulate and all other things, that is a signal. So that comes in the next stage. So these are basically the stage. Always remember, we do the first as a power planning, second as a clock planning, third as a data signal planning. And the stage wise also it will come in that particular way. So when you are doing the partitioning and all, at that particular time, we will say like, okay, block I'm placing here. So power planning. Then where exactly I'm going to place the standard cell. After that, only after that you're going to connect the clocks. So that means the clock. Then the third thing, whatever the remaining space and all other things, we'll do the data signal. After that, you're going to do the power and timing closer. So this is like when you're going to place the different standard cells, you have connected the clock, you have connected the signals, data signals, you have done each and everything. Now it's just a matter of power and timing. You have to just check this particular part. So here I've just mentioned timing in a power closer. That means at this particular stage is going to be closed. So it's just like in a sign off. Okay, before the sign off, you're going to close it. Now that doesn't mean power and the timing things we are not going to do in the rest of the stages. We are going to do it, because if we are not going to do it here, okay, so I was saying, if we're not going to do at this particular stage at different stages, then what will happen? There may be a possibility that when we will reach at the end of this particular stage, we have to go back to fix the timing, we have to go back to fix the power. So it's very important to make sure like there should not be any power related issues or the timing related issues in any of the stages. So now there are the two terms I just want to introduce here. The one term is a optimization and one term is a closer. So if anyone is going to use it, the power optimization or the timing optimization and the timing closer. Now optimization term we usually use when the tool do it automatically. So we tell the tool like, okay, we want to optimize the timing. So we just give the certain inputs. There is an automation. On the basis of that automation algorithm, tool is going to optimize the timing. Where the tool will say like, okay, you have given me 10 hours. In this particular 10 hours, I have tried everything. And after trying, now this is the optimum result. Either you give me the more time, then I will more optimize it. Else, now it's up to you whether you want to take it to the next level from here or not. So if you will say, okay, you have optimized it enough, now rest of the portion I will do manually. I will close it. I know where is the issue. Okay, so that comes as a part of a closer. So if you will say like, okay, now there are basically, you gave the tool 10 different conditions, like, okay, my timing should meet this much. This particular function supposed to be happen within a 10 nanosecond. Here 8 nanosecond, here 7 nanosecond. You give all these combinations to the tool, and the tool is just working on that particular part, just trying to fix that particular part. Now what happened? Tool is able to fix, tool is saying, okay, with this particular placement, you are able to achieve the 10 nanosecond, but you will not be able to achieve the 6 nanosecond. Then you're saying, no worry, I will do it myself, because I know you will do it, but I know your algorithm, you will take another 20 hours, but I know the problem, I will just fix it just right now, just typing certain commands. So that comes as a part of a closer, and the tool is going to do automatically, that comes as a part of a optimization. Okay. Yeah, so this is a VLSI general flow. And then now all the stages one by one, I will just help you out. Okay. Quickly, if you guys just want to go for any break, that is okay, or just want to take a break, or if you have any question, please, you can ask the question right now.
सर फैब्रिकेशन के बाद जो चिप फेलियर की जो रीजन होते हैं उसमें मोस्ट क्रिटिकल पॉइंट फैब्रिकेशन होगा.
Hello, sir.
Yes, Rabbani.
Yes, sir. Sir, if the constraint is given, like you have to design the circuit with respect to the speed only, so then it will be easy to it will be easy for me to know the PBT.
Okay, so Rabbani, what Rabbani is asking, Rabbani is saying, okay, if I will decide, like, okay, I have to design my circuit only for the speed purpose, okay, not the power. is it something is easy for me to decide the PVT corners? Am I right? Rabani, that's your question. Am I right?
Yes, sir.
Yeah.
Yeah, sir,
Sir,
we can
then
decide
there
it.
will be no difficulty
No,
for
no, no.
worst
So
case
this is the
corner.
difficulty. So all what you are doing. So I gave you the 5 different scenarios. I told you there are the different worst case for the power, different for the timing. In the timing also there are the different type of violations. Then I talked about in terms of the combination, like okay, they have the interdependency. Then I told you like okay, the portion of a circuit, the worst case combination is different. Some other portion, the worst case combination is different. So complexity remains same. All these things remain same. What you have done, you say like, okay, I don't care about the power numbers. So that means in the power case, even if it is a worst, if it is a best, I don't care. Even if my laptop is going to consume the power in such a way, like, okay, within a 1 hour, it is going to be like drain out. I'm okay with that. So I am not going to give the priority on the power side, but yes, timing is my priority. So what you are doing, you're okay with any kind of a analysis on the power side. So whatever the PVT, at least it should work. That's all. So for you, even if you are not going to check it for a particular PVT for the power, you're okay with that. So you are reducing the complexity, but that doesn't mean there will be no issues. So issues will be there, obviously. Abhi clear hai?
Yes, sir.
Okay, great. I think someone else was trying to ask some question.
सर तो ये सेम प्रॉब्लम हम कवरेज में भी होगा ना कि हम इतने सारे मिलियंस ऑफ ट्रांजिस्टर के साथ काम कर रहे हैं और काफी इनपुट हम मतलब एज पर मी कि हम सारे इनपुट चेक करने बैठे तो 2 साल निकल जाएंगे टेस्ट पे, बट हम कुछ कुछ ही कवरेज लेते हैं, तो वो कवरेज हम कैसे डिसाइड करेंगे अगर वर्स्ट केस भी हम केस डिसाइड नहीं कर पा रहे हैं तो?
Okay, so let me rephrase the question. So she is just asking the question from a different angle. She is saying like, okay, like in a case of a ATPG, automatic test pattern generation, or we are talking about the test bench where we are doing the logical verification or maybe the testing at the end of the design. She's asking like, okay, I have used one terminology, the coverage. Like, okay, am I able to cover all the scenarios to test it? Okay, so she is asking like, okay, in terms of the coverage, how we are going to define it? Like, okay, this is going to be 100%. Am I right, Pooja?
Yes sir, yes sir.
Yeah. So first of all, when we are talking about like, okay, whether the coverage is 100% or the 99%, so there is a different not the algorithm, but there are the different cases are there, and in that particular cases we check it like, okay, if this particular pattern is giving me this error, for example, some pattern is giving me a error at a location A, then we see like the same pattern can give me an error in location B also. So first we identify like, okay, how many places we can get the errors. Then we see like, okay, what are the patterns? There are the chances of the errors on these locations. So let us suppose in your design, let us suppose there are 2000 different points are there. Tomorrow, if something will break down, then you are sure like, okay, out of these 2000 points, somewhere there is a problem. Am I right? Or point in the sense, let us suppose there are the 2000 gates are there. If I'm saying your output is not proper, that means from the logical point of view, you have to go back and you have to trace the output of each and every gate, which is like 2000 gate. You have to check it, why the output is not coming proper. Am I right? So the moment you will identify the output of this particular inverter is not proper, then you will say, okay, there is a problem in this inverter. Now, to figure out the error at those 2000 logic gate, You're not supposed to apply millions of inputs. You will say like, okay, maybe with the help of 1 lakh of inputs, I can cover all the 2000 gate. That means if there is an error at the output of a inverter, so that error I can identify with this particular test pattern. 1 and the 2, these two test pattern can tell me, okay, there is an error at the output of this particular inverter. So I have to figure out those two test patterns, which can tell me like, okay, this is going to give me the error at the output of that particular inverter. Similarly, maybe to figure out the error at a particular input, you need 5 patterns. To figure out the error at a particular output, maybe you need 10 patterns. So in that particular way, you come up with the one set of a pattern, maybe the 1 lakh, 2 lakh, or the 4 lakh different patterns in a particular sequence. And if you will give all those patterns in that particular sequence, and everything is working fine, you're getting the desirable result. That means there is no problem. But if you're not getting the desirable result, you know, like, okay, which particular sequence is creating that a problem. That means there is a problem at this particular stage. So when we are talking about the coverage is in this particular way. So we are not saying the coverage in terms of the inputs. Now we change the problem statement. We are saying the problem is going to be inside the design. So let's figure out how we can identify the problem inside the design, and for that, how many patterns or the sequence I needed. So they're going to be defined set of sequence, or the defined set of patterns will be there. So that means you don't need a unlimited patterns of the sequence. Now you are limiting that particular part. So once you're going to figure out those things, that means your coverage is 100%. Is it clear?
Okay, sir. Yes, sir. Yes, it's clear. Yes, sir.
Okay. Good. So now quickly, let's talk about what is the RTL design and integration. So the important thing in the RTL design and integration, this particular flow. So in the before the break, we talked about like, okay, they're going to the RTL description, functional verification, logic synthesis, gate level netlist, and the logic verification come into the picture. Now let's see what exactly we are doing. RTL development. So ideally, when I will give you a problem statement, like, okay, you have to design this particular chip. So ideally, you're supposed to write the Verilog code. And that is known as a RTL development from the scratch. The first time in your life, you're going to write a code like in a module something. Okay. That means you're writing everything from the scratch. That is known as the RTL development. But now here we are not talking about the RTL development of a FIFO, or we are not talking about the RTL writing for a just traffic light controller. If I will ask you, like, okay, you have to write a RTL for a whole ALU design or the microprocessor, then you will say, like, okay, why should I write everything from the scratch? Because there are the couple of RTLs already available in the market. You will say, like, adder RTL is there. Why should I write a adder RTL? I will just pick this particular RTL. I will use it as it is. जो पहले से किसी ने लिखा है आप उसको as it is करोगे. But to go to that particular stage, first you have to break down your whole problem statement. You will say, like, okay, there is a processor. Inside the processor, there is a ALU. Inside the ALU, we are supposed to do the adder operation. Now this adder operation, now you have done the partitioning. You said, like, okay, now I'm going to write a RTL code for this adder. That is not the partitioning at the RTL level. So now I have done that particular part. So once you identify, once you do the partitioning, then the second question comes whether the code is already available or not. Then you will say, like, okay, I will take the code, I will use that particular code as it is. But then the question is, that adder is of what kind? What is the specification? What that code, what exactly it is doing? whether that code is compatible with your specifications or not. How you're going to identify that particular part. So to identify whether that particular code is compatible with my specification, you have to read it, or you have to understand the constraint of that particular code, RTL code. Constraint in the sense this RTL is going to give you the result after 1 nanosecond. I'm just taking a timing constraint. This RTL is using only 10 gates. Now you will say, okay, I need a RTL who's going to give me the results in 5 nanoseconds. So that means that becomes your constraint. So you need a adder which will give you the addition operation in a 5 nanosecond. But the available one is for the 10 nanosecond. So these are the constraints. So that means whatever the RTL you're going to write it, whatever the RTL you're going to do the partitioning, you have to understand, you have to do the partitioning of not only the logical side, you have to do the partitioning from the specification side also. So there is a whole ALU, it's supposed to be finished its operation within 30 nanosecond or 30 seconds, let us suppose 4 seconds. Now you have divided that 4 seconds into the nanoseconds. Like, okay, this particular portion supposed to do the addition in a 10 nanosecond. So now you need an RTL. RTL is what? RTL later on you're going to convert into the circuit. That particular RTL should give you the result in a 10 nanosecond. Another constraint is in terms of the input. There is a RTL for a 4 input adder, but you need a adder for the 16 input. So that is also a constraint. That means in one case there is a 4 input, in another case there is a 16 input. So these are the part of a constraint. So either you're going to, obviously you're going to develop the constraint, or whatever the constraint is already defined for a particular RTL, you're going to use it, that particular part. And that comes as a part of a RTL integration, the constraint checking. So whatever the constraint I have, whatever the constraint of the available RTL, whether those are integrating, matching with each other or not. If it is matching, it is good. If it is not matching, I cannot use this particular RTL. I have to write a new RTL. So that's what the RTL development or the RTL people doing nowadays. Okay, is it clear, everyone? Online people?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Now you have done the RTL integration checking. That means at the end of this stage, you have certain output files. In output files, you have all the RTL netlist, those RTL netlists which you have developed, or maybe you have just borrowed from someone else. Then you have the constraint of each and every RTL, means whatever with the blocks or the partitioning. So if I'm saying like, okay, there is a RTL netlist with in terms of the block, the partitioning which we are talking about, the block 1 to block n, then I have a constraint for all the blocks, and there is going to be like top level block design. So design constraint and your block level constraint, you will have all these things. Am I right?
Second question.
Mm-hmm.
So if I say block level, then we can say that the RTL is a hierarchical design for 2 type of RTL, flat or hierarchical, right? So अगर बहुत सारे ब्लॉक में तो हम ये बोलेंगे कि हमारा जो RTL hierarchical level का है ना सर?
टॉप लेवल हमारा डिजाइन, हमारा जो डिजाइन है वो हिरार्किकल लेवल का है। हिरार्किकल लेवल क्या होता है? So to understand the hierarchy, basically we are considered it from the organization. There is a manager. Okay, so in your college, what happened? There is a director, then there is a HOD, then there is a lecturer, then maybe there is in a class they say like, okay, this is a monitor, okay, and then all of you guys will come into the picture. So lab assistant, okay, so these are basically the hierarchy. So you cannot just every time just go and just approach the vice chancellor of your university. There is a process, you have to just go in that way. So when we are talking about the hierarchy in the design also, the hierarchy come in that particular order also. So I have a slides. I will tell you like, okay, what are the different kinds of hierarchy, logical hierarchy, physical hierarchy, then you will come to know. Okay, so now let's talk about like, okay, now you have the blocks, Now you have to work on each and every block separately. That work in the sense you have to, this is the RTL code, you have to convert each and every RTL into the circuit. So each and every block. Now you're not going to work just like that to the whole RTL. So one block means one RTL. Convert it into the blocks and into the circuit. So conversion of this, how you're going to do it? You have a design first, that particular code. You have to translate that particular code into the some unoptimized representation. Unoptimized in the sense, maybe you have written and an inverter. So it will say and an inverter only. And then after that, there is inverter. Optimized one is convert that and an inverter into the NAND. So unoptimized in the sense, it is just like whatever you have written, it will just convert into a intermediate representation. Then it will work on that particular part and it will give you a first level of gate level netlist. Like I said, one going to be and an inverter. Then it will optimize it, logically optimize it. So the moment it will see like, okay, there is a AND gate and after that there is an inverter, then they will say, okay, I can optimize it and I can say, okay, this become a NAND gate. So that is known as a logical optimization. It will do the logical optimization. And after the logical optimization, it will give you the second level of gate level netlist. So that means when you are talking about the logic synthesis, logically, first it will convert your code into a first level of circuit. Then it will logically optimize it. And it will give you the second level of gate level netlist. That becomes basically your final netlist, not the final, pre-final netlist. Now, depending upon your constraint, depending upon your technology node, depending upon your design. So if you're talking about the standard cell library, we're talking about the 40 nanometer or the 28 nanometer library, or plus whatever the constraint you have applied, what the tool is going to do. So here there is at this particular stage, there is a NAND gate, let us suppose. So if you remember, I told you as a part of a standard cell library, like, okay, in a 40 nanometer, they're going to be standard cell library where it is written NAND gate 1, they're going to be NAND gate 2, they're going to be like NAND gate 10 different type of NAND gates are there. Now, this NAND gate supposed to be map in the sense, this NAND gate of what type? So right now, this is just a symbol. You don't have it logically, everyone knows 0, 0, 0, 1, 1, 0, 1, 1. That is basically the NAND gate. But when we are talking about in terms of the delay, in terms of the power, then out of this 10 different NAND gate, which one you're supposed to choose? Who's going to decide? So tool is going to decide based on your constraint, whatever be the constraint you have provided here. And these constraints can be power constraint, physical constraint, timing constraint. On the basis of that, it will decide. So that is known as a part of a optimization. Now this NAND gate can be mapped with the NAND 1 or can be mapped with the NAND 10, depending upon the specifications of this and the constraints of your design. So that means once this optimization is done, then you will get optimized gate level netlist. And here, like I said, .lib. Now you're going to apply the .lib. .lib is what? Standard cell library. Now this standard cell library, I will explain you later on. There are, when we are talking about the technology libraries, so these libraries are can be of two types, physical libraries and logical libraries. Physical libraries has the physical information, logical libraries will have the logical information. We'll talk about this later on. Okay, so right now the point is you're going to provide this particular part. It will see the constraint, check with the library, and then it will give you the optimized gate level netlist. And this, the whole flow, this translation to optimized gate level netlist, this is basically the part of your logic synthesis. So inside the logic synthesis, you will do, or the tool will do all these things. Any question, any doubt?
No, sir.
Yes or no?
Sir, no, sir. No doubt.
No, sir.
Okay. देखो अभी तो नो बोल रहे हो, बाद में ये मत बोलना कि समझ में कुछ नहीं आया.
Sir,
Yes.
sir, like when we write a Verilog code for any logic, we only tell about what kind of a logic, like AND gate, NOT gate, how I would be implementing it. So, sir, like you said that it would be optimizing on the on the constraint, based on the constraint. So, sir, these constraints are about the delay of that gates, like physical constraints, or it is about something else?
Anything. Usually like power constraint, timing constraint, physical constraint. So we'll talk in the next slide when we talk about the logic synthesis. So there, even in the logic synthesis, there, I think you have already gone through. There are the two type of synthesis. One is a physical aware synthesis, another is a general first level synthesis. So if it is a first level synthesis, it don't have the physical information, then it's maybe like timing constraint is more than enough. And maybe the power constraint also you can give. But if you're doing the physical aware synthesis, then the physical constraint also come into the picture.
Yes, sir. And so second thing, the RTL code which I have written, it is not 100% like it can be converted into a real time hardware. So, sir, where it is checked, like in this translation process, it is checked right now or after that it is checked?
So Weber, basically, whatever the RTL you are going to write, at least that should be logically correct. Functionally that should be correct. Am I right?
Yes, sir. Yes, sir.
Yeah. So so that's the reason, if you will see, as a part of a front end, I have mentioned very clearly, there are the two type of verification we do. First is as a functional verification. So when you're going to write a Verilog code, the verification which you are going to do, that is a functional verification. That functionally it should work. If it is not working functionally, then you have to fix it at a Verilog stage itself, RTL stage itself. Okay. Logically, after this synthesis, we'll check it. Logical verification. We'll do the logical verification. That means logically it should work. Then the third thing which you're asking about, hardware point of view, whether it can be implemented on the hardware or not. So that comes later on. So if we can implement it, we will move forward. If we are not able to implement it, we will go back and we will ask the RTL engineer, like, okay, I'm not able to implement it on a hardware, change the RTL. So maybe the next slide will help you out. Okay.
Okay, sir.
So now the same question what Weber was asking, let's try to understand from the logic synthesis and optimization. What is the loop is there? So synthesis is there. In the synthesis, now there is a translation. There is a logic optimization. There is a gate level mapping. Now what happened? You have certain logic. You're going to translate it into the first level of netlist, first level of circuit. Now this first level of circuit, it is not mapped with any particular technology node. It is a pre-optimized circuit. Then you are going to optimize it logically. You will say like, okay, now this is something logically I'm going to optimize it. Same first level, then logical optimization, then the second level. So this is a circuit after second level optimization, logic level optimization, second level. Then you are going to map it with the technology node and you will get the final circuit. Now in this particular technology mapping and optimization, now let's try to understand what happens. So this was my flow: translation, logic optimization, then technology mapping. Once you will do the technology mapping, so right now I'm just checking as a timing optimization. So this class, this portion is related to the timing. So I will just more focus on the timing part, but the same flow, almost the same flow goes with the power side also. So now let's talk about the timing optimization. So in a timing optimization, what I'm going to do it, I'm just saying like, okay, I'm going to do the timing analysis, which is a static timing analysis. That means after the synthesis, once it is converted into the circuit, now that particular circuit, that particular NAND gate is mapped to a first level of any NAND gate. So let us suppose that NAND gate is mapped to the NAND 1. Then the tool is going to do the timing analysis, whether it is meeting the constraint or not. Timing analysis is what? It will do the timing analysis, it will check it, okay, how much time it will take to give you the output. You gave the constant as it should give me the output in the 6 nanosecond. So tool figure out like, okay, using a NAND 1, it is giving me the output in 10 nanosecond. That means there is a issue, there is a gap. It's supposed to work in a 6 nanosecond, but right now it is giving me the result in a 10 nanosecond. So that after the timing analysis, it will figure out like, okay, whether it is pass or the fail. If it is yes, if it is passing, then it will go to the next stage. If it will not pass, then it will say like, okay, now I have to make changes. Now what changes is going to do? It will say like, okay, NAND 1. We use the NAND 1. Now let's try the NAND 2, NAND 3. So this mapping which we are doing, it will change in the mapping portion. It will say like, okay, let's do the mapping. Remapping. In place of a NAND 1, now use the NAND 2. Then it will go back. Then it will do the same thing. NAND 3, NAND 4, NAND 5, NAND 6. Any point of a time, if it is matching, then it will go to the next stage. If it will not match, then it will just keep doing this particular part. Now let us suppose there are the 10 NAND gate. You tried everything. Even after that, you are not meeting the 6 nanosecond. Then what is going to be happen? Then you will say, like, okay, with the NAND gate, now this is the portion where the custom and the standard cell base things come into the picture. Now in a standard cell base, you have the predefined 10 NAND gate. Now you cannot make any changes. Now if it is a predefined 10 gates, then what will happen? Predefined 10 gates, even after that, if it is not working, then you cannot use the 11th NAND gate. Then you will say, okay, do one thing, change the logic. So whatever the logic optimization tool has done, now you're telling the tool like, okay, this logic optimization is not working for me because we are not able to meet the timing numbers. Change the logic. Maybe go back and just do something else. So that means now we will tell the tool like, okay, do some other logic optimization. So you will say like, okay, change the circuit logically. Then it will go back, it will do the logic optimization. So it will do the logic optimization, some other logic gate will come to the picture. Then again, you are going to do the mapping. The tool is going to try to meet that 6 nanosecond. If it is meeting, is good. If it is not meeting, then you will say there is a problem. I changed the logic. I used all the library cells. Even after that, nothing is happening. I cannot meet the 6 nanosecond now. So this is the place where now we are telling the RTL engineer like, okay, see, whatever the constraint you're talking about, I cannot meet the constraint. So change the constraint number. That means in place of a 6 nanosecond, give me the 7 nanosecond, 8 nanosecond. Something like that, you have to do it. Am I right? You cannot meet. So there are only two things. Logically, you can change it. You change the logic. You can say like, okay, I use all the NAND gates, cell gates, whatever in the mapping, both are used. Now what we have to do? Hey, I cannot meet it in the 6 nanosecond. I tried each and every combination, change the 6 nanosecond. They will say, okay, let's go with the 8 nanosecond. Now with the 8 nanosecond, if you are able to meet it, is good. If they will say, no. We cannot make any changes. Max to max, I can give you 7 nanosecond. But again, you will try each and everything. But even after that, after changing the constant, if things are not working properly, what does that mean? What is the stage previous that? is basically the partitioning of the RTL, because you did the partitioning, and that's the reason this you have written the constraint. Now you will say, like, okay, that means at the partition level, I have to make certain changes. Maybe I will not do the partitioning. I will merge the two RTLs. And then we'll see, like, okay, so basically what can happen? One RTL, it has a, let us suppose 8 nanosecond, another having the 6 nanosecond. If you merge both the RTL, overall, it become 8 plus 6, 14 nanosecond. Maybe you are able to meet that 14 nanosecond. Because in this 6 nanosecond, meeting the 6 nanosecond is very difficult. But here in a 8, you're meeting it as a 7. So here there is a margin of a +1. Here there is a margin of a -2. Maybe when you're going to combine it, it become 14. Maybe there's some logic changes you have to do it. So that means at a partitioning level, you have to make certain changes. So that again, the responsibility of the RTL. Who is going to do the partitioning? They're going to do, you just ask the RTL people, like, just makes these changes. After merging, repartitioning, everything you have done it, even after that, if it is not working, then you will tell the people, like, okay, see, there is a problem. Change everything, change the functionality itself, okay? Because with this functionality, with this particular specification, with this particular technology node, I'm not able to meet the things, make changes somewhere else. So maybe either they will relax certain constraint, they will say, okay, with this power number, you cannot meet, this timing is not sufficient, we will change the clock, or maybe we'll change something else, or maybe they will change certain design itself. So they will do all those things. So this is basically the part of timing optimization. So this should be the step. Now in this timing optimization, there are the two portions. One is the synthesis tool will automatically take care. That synthesis tool will take care after the translation. That means the first and the second is a part of a optimization. The tool will take care automatically. If there is anything in terms of the correction in the constraint, repartitioning of the RTL, all the logical changes, these are the something which you have to talk to the RTL developer separately, and you have to tell them, like, okay, yes, this you have to fix it. So there is always a iterations. You have to talk to the previous team, they will fix it, then it will come. So in the RTL stage, a lot of things happen, a lot of iterations happen. So Vaibhav, your question was something similar to this. Like, okay, how we are going to do this particular part? So in optimization, we'll see if it is a timing, at which stage we are making certain changes.
Yes, sir.
Okay, now if everything is working, then you will go to the next stage. After the logic synthesis, the next stage was the design planning. Am I right? So in a design planning, you will go. Design planning is what? It's the same floor planning. But here also, there are another next level of synthesis, which is known as a floor plan aware synthesis. So till now, we are talking in terms of the circuit. Now, what will happen in the next stage? This is the place where you are going to give the physical constraint. Before this, power or the timing constraint. But this is the place where you will give the physical constraint. So what will happen? RTL description, user defined physical constraint, you will do in this particular way. So this is the first level. Here you will define something. You will say, okay, this is the physical constraint, do the default synthesis, initial gate level netlist, implementation tool, floor plan. In a floor plan aware synthesis, or also known as a second two-pass synthesis. Okay, so that two-pass synthesis, maybe people have used that terminology. So here what happened? Now we are saying, okay, floor plan is already available. Floor plan in the sense the size of the chip is already there, which anyways we have the size of the chip. It's not like, because as a part of a specification, we always have the specification of my chip also. The chip is supposed to be this size, rectangle, square, L shape. We have that particular part. So what is going to be happen now? Whatever be the analysis you have done, you have to make sure, okay, in this particular floor plan, it is working fine or not. Now, question is how? So think in this way. This is your floor plan. Till now, we were saying like, okay, here I'm going to place a NAND gate. Here, there's going to be a inverter. Okay. Now, when I am saying like, okay, there is a NAND gate and there is a inverter. See the difference. In a first pass synthesis, you have done the analysis based on the information you have with respect to the NAND gate and the inverter. And the information of a NAND gate and the inverter is going to be present in a standard cell library. So what the tool is going to do, whatever with the information is present in the standard cell library, it will extract that information. It will do the analysis on the basis of that. Am I right? But here in the design, apart from the NAND gate and the inverter, there is something known as a wire. Till now, you were saying 6 nanosecond. You are saying, okay, 4 and the 2 is good. But what about this wire? When the signal will travel from this point to this point, it will take some time. Now, the question is, am I supposed to place this inverter here? Or can I place this inverter at this particular location? If I can place this inverter at this particular location, then this delay is going to be less. If I have to place this inverter at this particular location, the delay is going to be more. Now, who is going to restrict you? Who is going to force you to place this particular inverter at this particular location? That comes from the physical constraint. Maybe there is a physical constraint, and that physical constraint is saying like, okay, because of that particular physical constraint, you have to place this inverter at this particular location. Maybe. You never know. So the point is physical constraint. Now, maybe let's try to understand like, okay, what kind of physical constraint I'm talking about. So I'm saying this is a NAND gate, this is a inverter. This is a pin A, this is a pin B. I gave you a constraint that the pin A is going to be here only, and the pin B is going to be here only. This is the constraint, which is a physical constraint. Physically, in your chip, one pin A, is supposed to be the top corner, pin B is going to be bottom one. Now, why this constraint is there? Because this chip at the end of the day is going to be the part of a bigger board. And in that particular bigger board, the input is coming from here and you just need an output at this particular location. Because that is a PCB board. In that particular PC board, the location of each and every port is defined. So now the thing is, this is a constraint that pin A is supposed to be here, pin B is supposed to be at the bottom one. And this is the circuit. So that means this physical constraint you have to meet. Now you have an option like, okay, AND gate, either you will just put the AND gate here and the inverter here. Or even if you will say, like, okay, no. So why can't we just do it in a different way? I will just put the inverter here and I will just like combine this. Or maybe I will just put the whole system here itself. But this is something is you have to try. Then you will say, like, okay, in which particular case there is a bigger delay, in which particular case there is a lesser delay. Now, who's going to try it? Obviously, the tool is going to try that particular part. But for that, tool should have the wire delay information, because the wire delay is playing a very important role. Maybe that tomorrow you will say, like, okay, no, this is not going to work. The inverter I will place like this and everything is good. So that is the importance of floor plan aware. Now, if you will say, like, okay, with this particular combination, it is not working, let's use the inverter, which is going to have a lesser delay. So now the configuration which we have used it as a 4 and the 2, now you're saying, look, no, it's not going to work. Let's use the 3.5 and the 1.5, because once we will use this combination, it is become 5.0. And I have a 1 nanosecond, that 1 nanosecond is going to be considered as a part of a wire delay. So that means now you're changing, you're optimizing your circuit. And that is the importance of this particular floor plan aware synthesis. Okay, great. Good. Floor plan aware synthesis. The same floor plan is coming, second pass level. Then we'll do the placement, CTS routing and other stages.
सर दोनों सिंथेसिस तो सेम टूल से होंगे ना?
हाँ, दोनों सिंथेसिस मतलब टूल्स के लाइसेंस अलग अलग होते हैं. सेम टूल में उन लोगों ने पहले डिजाइन कंपाइलर था, अभी डिजाइन कंपाइलर टोपो करके यूज करते हैं, तो वो एक्सटेंडेड वर्जन है. मे बी यू डोंट वांट टू डू इट, सो दैट्स बेसिकली द मार्केटिंग थिंग.
क्योंकि फ्लोर प्लान से पहले दोनों सिंथेसिस होना कंपल्सरी है ना?
हाँ. Okay. Is it clear, guys, till this point? Any question? Online people. Niti ma'am, any question? Bhaskar sir.
No, sir, clear.
The
Okay. Okay, let's talk about the partitioning. So when we were talking about the partitioning at that particular time, I told you like, okay, partitioning is like dividing the design into the sub design, the small blocks. Okay. Now the question is how you're going to, why you're going to design, why you're going to do the partitioning. So partitioning, we are going to do it workable size. We are going to do it to meet certain physical constraint. Okay. Time to market, we just want to do it very fast. Maybe today I'm going to do it as a partition, and I'm going to design it, that particular partition, and I just want to reuse that partition again and again. So in the sense, today I did the partitioning for analog to digital converter. Tomorrow, again, I'm going to use the same analog to digital converter as it is, because nothing is going to change there. So it's basically, I can reuse that particular part. So today I have to design it, but tomorrow I can reuse it. Same goes with the memories also. Today I have to design it, tomorrow I can reuse it. Then there is a concept of a clock domain, power domain, functionality point of view. Power domain in the sense you want to run, basically in your circuit, power point of view, you are saying like, okay, one portion of my design, I will run on a 1 volt, another portion I just want to run a 0.8 or the 2 volt, anything. So you just dividing the whole chip in a different power domain. Same clock, one portion you want to run on a high frequency, another low frequency. That's your requirement. Okay, so that means different clock domain. I just want to do in that particular way. So these are a couple of portions, like, okay, how we do the partitioning. Now power related, now people are talking about the hierarchy. So in terms of the power domain and hierarchy, logical voltage domain hierarchy. So what is the hierarchy thing? So they're going to the top level design. Within the top level, maybe you have divided into the A1 and A2. You said like, okay, these two are going to have it to different power. Within the A1, there is a B11, B12, similarly like A2, B21, B22, and B23, same. So you can have multiple hierarchical things. So the left-hand side is basically the logically, left-hand side is basically in terms of the graph, you can see it. Okay. But physically, if you will see, physically is like this. That means the one important thing is in the top, A1 and A2 are 100%. Okay. So that means A1 is here, A2 is here. These two, A1 and A2, those are the two separate ones. Now inside A2, there is a B11. So B11 supposed to be 100% inside the A1. It should not be like, okay, you will say like, okay, this is a B11. No. So this is not allowed. B11 supposed to be inside the A1. So that's the reason we are talking about as a physically hierarchical design. Now then, if it is a voltage point of view, power point of view, clock point of view, whatever the hierarchy we are creating, we can have the different structure here. Like here the power B12 is of a different voltage domain, B23 is a different voltage domain, this is a different voltage domain. So you can have the any combination. This is in terms of the voltage, that is in terms of the power. Okay, so then we have the concept of the level shifters. So we'll discuss this particular part later on. Okay, this is in terms of the hierarchy, functionality point of view. So you can say, like, okay, functionality point of view, I'm going to divide into the different hierarchy. Like, okay, one portion is going to be for HDMI, USB. Another portion is in terms of the transistor, transmitter, or the receiver. One is basically the DSP, A to D. So these are, when I'm saying these are basically in terms of the functionality, I just divide and I created a hierarchy. You can create in terms of the same, the power also. So this power related thing, this is the functionality related thing that depends on you. Like, okay, how you're going to create the hierarchy. People are doing creating the hierarchy like clock hierarchy, power hierarchy, in terms of the functional hierarchy. They're doing all these combinations. So hierarchy is basically, there is a top, inside this there is a small block, inside that there is another block. So it can be like a 2-level, 3-level, 4-level hierarchy. So right now here, if you will see in the functional case, it is a single level hierarchy. Top, and then the rest of the thing is a block. Okay. So you're going to divide, you're going to design all these blocks one by one. If you will go in the previous one, here you can see white, then there is a black, one level of hierarchy. Inside the black, there is a blue. That means the second level of hierarchy. If you will go the previous one here, there is basically the 3 level of hierarchy. In the top, there is a A2, first level, A2, there is a B21, second level. Within the B21, there is a C211. There's a 3-level of hierarchy. So it depends, like, okay, how you want to design your circuit. 2-level hierarchy, 3-level hierarchy, 1-level hierarchy. It all depends on you. So once your partitioning is done, so in a physical design, what was the next thing? Partitioning, then the chip planning. Now the question is, what exactly we do in the chip planning? I told you, in the chip planning, we place these blocks, plus we do the power planning. So power planning in the sense, plus physical point of view, all the physical constraint, because we are defining the floor plan. So that means physically constrained in terms of the floor plan, where the particular pin supposed to be placed, what is going to be the size of my floor plan, what is the size of my chip. Okay, where are basically these stripes, where I'm going to place my standard cells, where I'm supposed to place my macros, or you can say the blocks, where exactly I'm going to doing the routing of my power lines. Everything comes as a part of a floor planning. So I think when you're going to discuss, when you're going to learn the PD portion, then you will able to figure out all these things. I'm just giving an idea. Okay, so these are the couple of terminology in terms of the port location, in terms of the cluster site array. This is my fixed cell. This is a keep out margin. So maybe you can ask Aditya or anyone, like, okay, what is the meaning of this? But they will explain you this particular part. Now, in terms of the floor plan, there are the two things, the core and the IOs. So core and the IOs, in the sense, if I will say, like, okay, this is my chip, these are my ports. So you're not going to connect these ports with the inside logic directly. So you have to create a boundary here. This is basically the, not the boundary in the layman language is the boundary, but these are the basically the IO port, IO pad. IO pad in the sense input, output, pad. That means whenever there is a communication inside to outside or outside to inside, it's supposed to pass this particular pad. And what is the use of this particular pad? There is a lot of uses, but one of the thing is inside, if I'm saying there is an input pin. Now, what is the meaning of input pin? There is going to be one diode. So that means this will work only in this direction. Output pin, there going to be one diode here. It will work in this direction. Current or the voltage will flow from this, voltage will go from this side to this side only. So now this become my input port. This become my output port. Now, if you will say, okay, see, I have a port which works as an input and output port. Okay, so let's do it in this way. This is my it can go inside also, signal can go outside also. But then you will say, like, okay, the signal will go like this also. No. So they're going to be a controlling signal. Something will be there here. Something supposed to be here. And these two things are going to be controlled with the help of a signal. So these are basically the gates, okay? So this gate, so it will be, if I will just draw the picture more clearly, it will be something in this way. Input, output, enable signal. Okay. So now you will say if it is 0, then maybe this is going to switch off, switch on. When it is going to be 1, then this is going to be switch off on. So in this particular way, you can control a particular port, whether it's going to be input and output. You can write a logic. Okay. First enable signal is going to be 0, then it is going to receive the signal. When the enable signal is equals to 1, then it is going to give you the output. So in that particular way, you can design your IO pad. So this is a part of one of the circuit inside the IO pad for each and every port. Then there is a something known as like, okay, what if suddenly from the outside one high voltage signal came up? That means some sparking, okay, something come up. So how you are going to make sure, like, okay, inside the like your chip, there should not be any problem. So like we have in our houses, like in a regulator, okay, not the regulator, what we say, some
MCB.
MCB is a one thing. Stabilizer, yes. It is going to stabilize your voltage. So same thing is here, like, okay, how much voltage fluctuation it can bear. And you will, whether the output will be there or not. Okay, so basically what I'm just trying to tell you, like at this particular, this IO pad will have all these things, depending upon your circuit, depending upon whatever you want to design. So there is a separate team, they do this IO pad related things. So that means now so what is happening now? Your chip, it has the IO pad and the core area. Now this is the slide for the core, how you're going to decide the size of your core. So that is a part of a floor plan. So now the top level thing, people usually ask like, okay, what is the meaning of size of the core? So there is a concept of a aspect ratio. Like, okay, what is the aspect ratio? So aspect ratio is like width versus length. Size. If the aspect ratio is 1, that means the height and the width is same. Aspect ratio is 0.5, that the height and the width is different. Is like width is more and the height is less. So this is the aspect ratio. So usually the code decide in this particular way. So either you will tell the tool like, okay, my aspect ratio of the core is this, or you will tell the size. You will say like, okay, some sizes there. You will just give the exact coordinate like, okay, this is L shape or something. I just want to create my core. Now, second question is, this is the ratio. So you say like, okay, whatever be my height, width is going to be the double of that, for example. But what is the exact number? How are you going to identify that particular number? So for that, there is a, okay, so let me just take it one step back. So let us suppose in your synthesis stage, there are the logic gates. You know the logic gates, okay? You place the logic gates at that particular stage. You already mapped all your logic gate with the standard cell library. Am I right? And I told you standard cell library has the two type of information, logical and physical. Physical in the sense, each standard cell has its own layout. So let us suppose this is the layout of your sum gate. So now you know what is the size of this. So that means for each and every standard cell, you know the size of that particular standard cell. So if I will say NAND gate, you can say like, okay, yes, NAND gate is going to take this much of area. Inverter is going to take this much of area. If there is a adder, adder is going to take this much of area. Flip-flop is going to take this much of area. Am I right? So let us suppose in your design, you are using 20 different type of standard cells, which has a logical gates, which has a sequential element, which has a combinational element. So if I will say like, okay, what is those 20? So let's take it in this way. I'm saying AND, NAND, MUX, adder. Then I will say like, okay, what is the size of this? You will say the size is X, Y, Z, and U. Then I will say like, okay, how many AND gate? You will say 100 AND gates. Now here, this is the 1000. MUX is basically only 10. Adder, we are use the 4. So this is after the synthesis data. Then I will say like, okay, how much area you need it? Then you will say like, okay, very simple. 4U plus 10Z plus 1000Y plus 100X. So this is the total area I need it. Am I right? Online guys, is it clear?
Yes, sir.
Yes, sir.
Okay, great. So that means this much of area, this much of a core area where you are going to place your standard cell. Now you know that particular area. So if I will ask you like, okay, now what? You will say like, okay, this is equals to a area A1. Okay, great. So now you have everything. Okay, wait. Now you have everything. You will say, Puneet, area is A1. A1 equals to height is X, width is 2X. That means X into 2X. That is the area. That means the 2X square. That means X equals to A1 by 2 ka under root. Now you can calculate X. You can calculate the height. You can calculate the width. Is this portion clear, anyone? Guys, yes or no?
Yes, sir.
Yes, sir.
Yes.
So now
Yes, sir.
now you know the size of your chip. Am I right? But this size of the chip is based on the standard cells only. Only standard cells. What does that mean? Only the standard cells. Now let's try to understand from the CMOS point of view. So CMOS is what? Basically, if I'm talking about, so this is my cross section. Okay, this is my substrate. How we place it? This is my N plus, then N plus, Okay, 3D model is something like this. Then you will select, okay, N will come here like this. Am I right? So this is a one gate. Then you will select, okay, another gate is like here it will come P plus, then again the gate will come this. Okay, and this thing is like this. So in this particular way, you know the area of this. Okay, so this is the wafer area. So this is basically the wafer area. So if I'm saying in the previous slide, I said now you have the X. So now you know, like, okay, this is my X, this is my 2X. And in this, if I have to place so many standard cells, you will place back to back. Okay, first standard cell will come here. This is maybe the AND gate. The another one will come here as a NAND gate, whatever the placement you will do it. Okay. So in this particular way, you will do it. And if I just want to see it on the top level, so the top level, basically, this is your chip. Now you're placing everything here. Is it clear, everyone? Any doubt? Online people, is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So in this particular way, what is happening? You are utilizing your wafer 100%. Because the way you have calculated the wafer area, you have calculated the wafer area from the standard cell point of view. So in a standard cell, after the logic synthesis, whatever with the standard cell count was there, then you say, like, okay, in this particular standard cell, these many AND gate, these many NAND gate, adder, multiplexer, we have used it. And on the basis of that, you have calculated the area of your wafer. This is 100% utilized. Now the question is, or the next thing is, now let us suppose tomorrow, if there is any issue. So there is a circuit. In that particular circuit, there is something known as inverter, or there is a NOR gate like this. So when you were doing the timing analysis, you figure out, like, okay, you have to add certain buffers. So I'm not asking you to add anything with respect to any logical gate. Logical gate in the sense NAND and all these things. But I'm saying maybe there is a requirement you have to add a buffer here. But this buffer was not a part of your logic synthesis. Because at that particular point, everything you are doing with respect to the logically part. But now you figure out, I have to add a buffer. Especially when we are talking about the clock tree synthesis, to meet the clock timing, sometimes we have to add buffers. Sometime we'll discuss this particular part. We have to delay my circuit data. Intentionally, we have to delay my data. So you have to add certain buffers. You have to increase the delay of your circuit. So how you're going to increase the delay? Maybe you are going to add a buffer. Second thing is, during the logic synthesis, even when you have done the floor plan aware synthesis, that was you assumed it. Like, okay, in the floor plan aware synthesis, this is my floor plan. There's going to be a AND gate here. There's going to be one inverter here. And this is going to be my delay of wire. But there is a possibility when you're going to actually decide, like, okay, where exactly going to be my wire, you would come to know the delay is more. Or maybe the delay is less. Based on that, maybe you have to further change this particular NAND gate. So right now, this NAND gate may be using a area of A1. Maybe later on, you have to change it to the A1 plus delta A1, or maybe some A2 from the standard cell library. Now, how you are going to use or how you are going to place this extra buffer or make changes in the NAND gate if you have decided the wafer space based on the output of synthesis. Whatever the calculation we have done, based on that, you came up with a certain number, how you're going to make changes in your core area. So then the concept of utilization come into the picture, like, okay, everything is good. I have a core, and the size of the core is based on my standard cell calculation. But am I supposed to take it as a 100% utilize? So answer is no. I'm not supposed to take it as a 100% utilization. I'm supposed to consider that number as a maybe 0.7%, 70%, or the 0.7 utilization factor. That means the 0.3 or the 30% space of my wafer, I'm taking it as a margin, or I'm just taking it, okay, as a backup plan. If tomorrow I have to add a certain buffers, if I have to increase the size, at least I have something. Else it is going to be very difficult. I have to go back and I have to do the each and everything once again. So that's the reason this core size, when you're going to define the core size, now there are the two things. First, you have decided the aspect ratio. Then after the logic synthesis, whatever the gates, number counts are there, using the physical information where their approximate, not the approximate, their size is given. You will calculate the exact size. Then you will use it as a part of the utilization. You will say, like, okay, it's going to take only the 70%. So if your area was coming A1 from the synthesis, or you can say after synthesis, then you will say this A1 is basically the 70% of my final area. So final area is AF is equals to 70, or you can say like this, 70% of AF is equals to A1. Now you know the AF. So AF is A1 divided by 70 into 100. So now this becomes your AF, which is a final area. So this utilization factor, this is one of the utilization factor. How much utilization factor you have? People are using the 0.6 utilization factor, 0.85, 0.7, 0.9, depending upon their design, depending upon their understanding. If they know their design very well, they will say, okay, 0.9 utilization is good enough. If they are not 100% sure, they will say, like, okay, let's go with the 0.6 utilization factor. So now in this particular way, their core area is defined. Okay, great. I think, again, this is like size. Now you know the area. Now, if either you will just go with the width and the aspect ratio point, or you will go with this, you will select exact coordinates, and then you can just figure out. This is the physical constant. This is also the part of your chip planning, where you will say, like, okay, port N, port M, this particular pin supposed to be at this particular location, this pin supposed to be at this particular location. So this comes as a part of your physical constraint. So these are a couple of definitions in terms of physical constraint, like, okay, you can say, like, okay, this is the coordinates of my core, this is the cell location. Again, you are saying, like, okay, orientation or the cell location is supposed to be this, my port location, some keep out margin. You also say, like, okay, at this particular place, there should not be any cell. I'm going to keep it. That is a keep out margin. Some blockages are there. Like, okay, we'll say, okay, at this particular location, we are not going to keep any cell. We'll discuss this particular part as the blockages and all other things, some net shapes and all other things, because we are talking about the physical part. So these, everything is a part of a floor planning or the chip planning. Any question, guys? Hello, any question?
No, sir.
No, sir.
Okay.
No, sir.
No, sir.
Good guys. So we'll stop the session here
Yeah,
itself. Okay?
yes, sir. Yes, sir.
Because it's like too much for you guys for today.
Okay.
But I
because,
think at least now you have an idea like, okay,